We can hear you.
Okay, so actually my internet connection right now is a bit unstable, so sorry, sorry for advance if my the quality will get worse. So yeah.
We can hear you fine, and we can see your screen.
Okay, that's good. Okay, okay. So can I start now? Okay.
Yes, go ahead.
Okay, thank you. So first, I thank you for organizing these great sessions. And today, I'm going to present our work on the artificial cognitive map system using deep generative neural networks. So let me start with a brief introduction of the concept of cognitive map. So cognitive map was originally proposed by a Tolman who studies the behavior of the rats, especially the rats solving mazes. And he found that the behavior was not like just a stimulus response, but more like they use some kind of internal representation, kind of map-like representation. And then after that, biologically, place cells and grid cells were found, which encode the kind of spatial position in the environment. And now many people believe that these cells are the biological implementation of the cognitive map system. Okay, so then how these spatial maps are organized. And then there's still some controversy, but now many people believe that this kind of spatial representation is constructed from the self-motion information. So here is an example. And so with the information, self-motion, the placer can nicely represent the spatial specific position. But without self-motion and just using a visual information, that the map was more disorganized and not spatial specific mapping was organized. Okay. And then also there are some models for artificial cognitive map system. And most of these studies are mainly using self-motion information. So here is an example from the Nochi and others. And then they use hierarchical recurrent neural networks. And they found that in the higher level of the recurrent neural networks, there appears this kind of a nice representation of the environment. Okay, but our approach was more like the opposite direction. And then people usually try to construct this type of nice systems, but more like we are going to create this type of disorganized system. And we think this kind of things might be related to the concept of this spatial sessions. So basically, we think that a deviation from the actual map is more informative when we want to understand the underlying cognition. So, this type of map just converts to a very nice representation of the actual map. So if we make a nice system, and even if that underlying system was different, usually if these things works, just converts to the same map, but then we cannot infer the underlying information from this map. But this time, this organized map, maybe we can characterize this map, and then we can understand the underlying information. So for that purpose, we use only the visual information to make our artificial cognitive map system, and then characterize the resulting maps. Okay. So for that purpose, we used generative deep neural networks, which was recently developed in this 4 or 5 years. And so here is the examples and the figure from the DC gang, which result in this type of decomposition neural networks. And if you input some latent vectors here, then this system generates nice images. So our idea is that this space of latent vector is somehow organized through the training. And this, the structure can be considered as artificial cognitive map. So this is our system. So basically, this was based on the architecture proposed by Larson and others, and called VA-GAN, and which is basically a combination of variational autoencoder and GAN. So this part is VAE. So the input image was encoded into the latent vectors and then reconstructed back to image by generator. And for the GAN part, there is a discriminator, which tried to recognize whether the input image was a real one or the reconstructed or generated one. And then I also made some modification to the original system to make this system predict the image. So usually, because this is autoencoder, usually if we input some image, we train the network to reconstruct this image. So this image should be equal to the generated image. But we modified this part and we train the network to output the image times ahead. So if we input the image of time t, then we train the network to output the image of t plus tau. Okay. And also, we want to check whether the presence of GAN affects the results. So we make two conditions, which are VAE and VA-GAN. So for this condition, this is just a variational autoencoder. So yeah, there's just a variational autoencoder. So the loss for prior and the loss for reconstruction loss is present. But for the VA-GAN, we add a GAN loss here, which is a loss for discriminator. And for the technical details, we use WGAN-GP for the GAN part. Okay. And for the dataset, we use this kind of very simple subjective visual information, which just walking around this type of edge-shaped environment. And then the agent randomly goes to right or go to the left at this bifurcation. Okay. And here are the results. And if you input this image, the generated image was not the exact copy of the input image, but more like the target image. Okay. So we want to understand the cognitive map. So in this system, this is corresponding to this part, which means if you input the image, it was encoded into the latent space vector here. And then, yeah, so we denote this as, if you input xt here, we denote this point as zt. And we investigate this structure to understand what kind of features are encoded here. Okay, so here is the actual maps of our system. So here, this is the VAE and this is the VA-GAN. And here is the input image, and this is the corresponding position in the latent space. And this is the output image, generated image. So you can see that actually the map was not so well organized and not much like the actual environmental shape of the edge shape. And also, this seems more smoothly and maybe more organized, but not like the actual edge-shaped environment position. So the result was, so you can see that the map did not directly represent the actual spatial coordinate. Okay, so then, so whether this was just a disorganized mapping, random mapping, or whether this has some structure underlying it. So to investigate that, we compared the distance matrix of the image and the distance matrix of the latent vectors. So for the distance matrix of image dataset, we calculate the difference between the image from the two image from the dataset, let's say xt1, xt2, and then we calculate the distance between these two, the pixel distance between these two by calculating the mean squared error between these two images. And then we calculate this for every combination of image, and we can get this type of distance matrix for the dataset images. And also, we encode these images into a latent space, and we can get the corresponding latent vectors, like the T1 and the T2, and then we calculate the distance between these two vectors by just calculating the Euclidean norms. And then we also can get this type of distance matrix. And then we compare these two to check whether these two are correlated or not by just calculate the correlation coefficient. And this is the result. And here is the correlation coefficient. And then we found that you can see that these two are actually very correlated. So actually that kind of disorganized mapping reflected the distance matrix of the distance matrix of images. And also, these green dots show the case of the prediction time of 30 frames ahead. And you can see that, okay, so this is the correlation to distance matrix of input image, but this is also we calculate the correlation to the distance matrix of the target or the kind of predicted images. And we found that actually the correlation of the distance matrix was higher in the between the target image and the latent space vectors. So actually, our map more reflected the features of the predicted image, not more on the input images. Okay. So here is the summary one. So we made the artificial cognitive map system using deep generative neural networks, and we trained to predict the visual input. We found that the distance matrix of the predicted image was actually reflected in the latent space. So that unseemly random mapping actually has some structure inside it. Okay. So next, I want to go into different features of the maps. So we want to think this as a kind of cognitive map system. So basically, the cognitive map was used for planning or navigation. So for that purpose, we want to explore inside these spaces. So the previous analysis, we input images and then we check the resulting structure in this latent space, but usually we cannot get the actual input image for the kind of features. So we want to explore inside this latent space. And for that purpose, we think that we want the map to have these, at least to have these requirements. So one is any latent vectors in the space must generate decent images, and then also the images generated from the two latent vectors should be smoothly connected. So if we go from this latent vector and going to a different latent vectors, we want the change through the trajectory, want it to be smoothly or naturally transitions. And these two are corresponding to random sampling and interpolation respectively. So this is an example of the result. And here is the result from the random sampling from the VAE. And this is the result from the VAE GAN. And you can see that the VAE output from the VAE was more blurry and not much like the actual scenery. But with GAN, the output was less blurry and getting more decent sceneries. And also for the interpolation, so we interpolate this image and this image inside the latent space and check the output images. And we found that with GAN, the images were very nicely transitioned from this image to this image. But in VAE, this was not much like smoothly connected. Actually, there only exists this image, and then just connected by superpose this image and changing the related component of these images. So with GAN, the image were more smoothly interpolated. And from that, we think that this type of map was more suitable for the cognitive map system. Okay, so the summary two. So with GAN, random sampling interpolation were enabled, and we think these features are very suitable or necessary for the cognitive map system. And at last, we want to show the sequence image generation by closed loop. And actually, we make the system predictive, so we can generate image sequence without its image by. So if we generate image, then this image can be encoded in the latent space using encoder, and then this can generate image, and then this was encoded in the latent vector. So this loop can generate image sequences. So this is an example of the resulting image sequences. So you can see that this video was generated without any input image during this generation, but they can internally replay the past experience. So this might be analogous to the replay in hippocampus. So we also classify the closed loop trajectory into three types, which are fixed point, limit cycle, and chaotic trajectory, like these. And we found that, so this is the result of the NOP prediction and mild prediction and long-time prediction. And we found that NOP prediction, the closed loop trajectory always goes to a fixed point, but with prediction, it can go to a limit cycle or chaotic trajectory. And also with GAN, the trajectory was more likely to go to a chaotic trajectory. So GAN enhances generation of more chaotic trajectories. Okay, so summary three, the system can internally generate image sequences. And with GAN, the system was more likely to produce chaotic, and maybe we can say this was a kind of novel trajectories. Okay, so here's some discussion. So we found that the seemingly disorganized latent space actually reflected the proximity of the predicted images. So maybe we can, so at this moment, we cannot say this was analogs to our system, but maybe we can provide some tools to understand this type of maps. And also, there are some papers which propose that hippocampus actually encoding the prediction of the system. So this might be related to this type of studies. And also, we think that mapping proximity like this and also ability to be explored internally might be a kind of a minimal requirements for the cognitive map or kind of generate cognitive maps. And then this type of generalization of the cognitive maps was not only useful to understand this type this seemingly disorganized maps, but we think that this can also be applied to understand the non-spatial mappings in hippocampus, which was have been reported recently, such as many studies show that the hippocampus actually encode not only the spatial coordinates, but also encodes sounds or simple drawings or even the social relationship were encoded in the hippocampus. And these type of non-spatial things were not necessary two-dimensional and more high-dimensional, and also there are no natural metrics. So maybe this type of generalization of cognitive maps is very useful to understand these type new cognitive map systems. Okay, so here is the summary, and thank you for your attention.
Thank you so much. Do we have some questions in the chat or in the Q&A, or you can also raise your hand if you want to ask your question by yourself. Yes, there is a question. Okay, here you go.
Hi, thanks for your talk, Hiroki. I really enjoyed it. I wanted to ask if you're aware of, there was a recent paper showing drift in the cortex. Wondering if your system or any future systems you design to implement, maybe the changes in sort of latent space that represent the cognitive map change with experience, and maybe, you know, one point in the latent space that represented a real point in the environment changes, even though it still relates to the same space, if that makes sense.
Yeah, even the drift is the kind of, during the learning, the mapping was kind of changing or?
Yeah, so that the same point in the latent space that represented specific points, let's say point A in the outside world, the actual position of it changes in relation to the other points, but somehow still is consistent for behavior. I can link the paper in the chat.
Oh, thank you very much. So also there are kind of long-standing discussion of in the place cells that actually place cells remap in during during learning or some contextual changes. So even so, and I think there are no nice explanation why this kind of remapping was occurred, and so yeah, maybe so yeah, these type of things are, I think, very interesting, and yeah, if there are some kind of underlying principle, that will be very nice. And yeah, thank you very much.
Thank you.
Do we have other questions? If not, I have a question. What happens if you ask the GAN to interpolate between two images where there is actually no path between these two images? Like you tell it to go through a wall or something. You're still muted, by the way.
Okay. So actually, maybe I wanted to show something. Oh, sorry. Oh, okay. Well, oh, actually, things doesn't work well. So actually, there are. So here is an example of the kind of image output from the kind of grid of the latent vectors. So actually there is a abrupt change in the latent space. So actually, if we go there, there are smoothly changes, but if you cross this kind of borderline, the output abruptly changes. So, but during that transition, it seems like there are no kind of blurry images like this. So yeah, so it seems like the, two types of connecting, one is smoothly connected, but if there are no path, it just abruptly changes from one state to the other, I think.
I see, thank you. Any other questions? We still have time for at least one, if anyone has a question. And if we don't have any questions, I think we should still wait a little bit for the next talk in case people are coming from the other session to this one. So we'll wait 3 minutes. We can discuss in the meantime. Well, okay, let me ask you another question. What's your next step with this research?
Well, yeah, that's a good question. So actually, so if we want to construct a nice artificial map system which encodes a nice representation, then if we construct a nice system and then nice scores, then the study was over. But this type of studies, basically, in order to say something, we have to systematically investigate anything that the system can represent and also characterize these features. So actually, there are a lot of things to do, like change the parameters and also finding a nice characterization of these maps. But yeah, so I think there are a lot to do, but I don't know how to, wrap up these things. Yeah.
Thank you. Yes,
maybe I think that is kind of, yeah.
Go ahead.
Things yeah, I think, maybe you're going to study the failure of the perception. So maybe this type, things is kind of common to this type of study because, we want